Red Bull just released the RB17. In this video, we're going to go from the front to the back of the car, having a look at how the aerodynamics work on this particular car. For those of you that are new to my channel, I was an aerodynamicist for Mercedes for the 2018, 19, and 20 Formula One seasons, and I now work as an aerodynamics consultant, designing race cars in all different classes all around the world. Now, there's already an interview with Adrian about the car in general. However, in that video, he doesn't go super into the aerodynamics. So we're going to look here a bit more at the specifics of how each aero device is functioning on the car. Firstly, let's talk about the downforce numbers on this car. Now, they've claimed 1,700 kilos at 240 kilometers per hour. Now, this equates to an SCZ of about 6.1-ish. The more interesting number is the efficiency that's being claimed. That's a claimed efficiency of 16:1, which puts the SCX around about the 0.38 mark. Now, given this is a 1,200 horsepower car, of which I think about 200 horsepower is electric, let's say that we're putting 800 kilowatts to the wheels roughly, that would give you a top speed in excess of 540 kilometers per hour. However, the car is limited at 350 k's per hour because of limitations of the tire loadings. To mitigate some of those, the car has active aero. We're talking an active rear wing, active diffuser, and active front wing that can back off with speed, so that downforce will bleed off at speed, although there's still going to be a significant component of downforce on the tires, increasing that tire load, meaning that you have to limit that top speed. Now, in addition to the active aero, there's also active suspension for platform control, and there's also been mention of some fans being used for active aero there. I'll go into the fans a little bit later with some speculation. What's interesting to me is that with a 900 kilogram car and these downforce numbers, they are claiming that this car can lap similar to a modern F1 car. Now, that's with considerably less downforce to weight than a modern F1 car. Yes, it's got better efficiency, but the power to weight's not that much higher, the top speed's not that different. So in terms of where they're generating their extra lap time from, I'm not exactly sure. Some of it might be the characteristic with obviously the active suspension plus the blowing. But the other thing that may be happening is these numbers that we've been presented with may be revised as the final version comes out, because this current version is an earlier development model that we're seeing. So we're not quite sure if the spec they're giving us now is what it's actually going to be to finish up. It's worth noting too that as we'll go through in the flow analysis, that there are a fair few number of styling features on this car. Adrian talks about in his interview the fact that there are styling details and aesthetic details on this car, and so it's worth noting that there will potentially be some minor aero hits here and there for styling compromises. So anyway, let's go into the aero analysis part of the video, and that comes with my usual disclaimer of no aerodynamicist can predict flows perfectly by eye. You need CFD and wind tunnel, etc. to try and work them out exactly, but I'll still give my best educated guesses as to what's going on. Aerodynamically, I think of this car as an evolution of the Valkyrie. It runs on very much the same sort of general concept as that car. You've got essentially a multi-element front wing floating around in free air with a large volume of open space behind it. You've got a relatively high degree of porosity up high, and then you have an outwashing element behind a largely exposed front tire. The floor then has two large entry tunnels that then go back into a big three-dimensional diffuser at the rear that has a lot of flow going inboard of the tire over the bodywork so that it goes in between that diffuser and the rear wheel. You then have a low-lying, low-set rear wing that has, in this case, the same sort of end plates that wrap around that are similar to something like the Valkyrie AMR Pro. But of course, there's been quite a few critical detail changes, so let's roll through this car as if it was largely a new car. So starting at the front wing, one of the first interesting details I want to just point out is this central support. You'll notice that it's only got a single support as opposed to a more traditional layout, which typically has two supports. Now, the reason why you typically have two supports on a wing like this is that during something like a rolling condition or something like that, what will end up happening is that this side of the wing will be lower to the ground than this side of the wing, and so you'll often end up with more suction in this area. Now, when you have more suction there, that will increase the downforce on this side of the wing. You'll get an asymmetric loading of the wing, and so you have two supports to try and cancel out that loading, because a single support would be much harder to get the structural stiffness in. However, this is a fully bodied car, so what it means is that you've got a whole bunch of support coming out this way in terms of this box over here that's also tied back over here into these wheel pods. And when you combine that with this little stay that ties into the end plate, you'll see that that allows you to increase the stiffness of this region in asymmetric supports and then just carry out the main vertical load through that center pillar. Now, why would you go to all this effort? Well, having just one pillar in the center means that you have less losses go downstream and enter your floor. If you have two pillars, you're getting losses off each of these pillars and they're going to go and find their way into the entry of your nice little floor tunnels. One central pillar means that you've got less loss overall, and it also means that loss is more constrained to the dead center line, which, given this car's tunnel layout, might be a little bit less sensitive to it. It's not going to be a huge gain or anything like that, but it is perhaps a subtle improvement. Now, aerodynamically, what we have going on here is we have a wheel blocker that goes fully in front of the front wheel. Then we have a flat area directly in front of here. You'll note it's not upwashing or anything like that. We have a small curled foot plate to the outside. And then we've got further inboard our cone region. So that's our cone there. And then we have a wing profile that just goes through the center. No Y250, no vortex generating features, anything like that. It's just clean and upwashing through the center. There's also a single delta end plate on each side. So let's go through each one of those features. Now, the purpose of the wheel blocker is obvious enough. It is to stop a large amount of high energy air impacting the fairly square and fairly flat face on the front of your tire. If you have this air impact, you get a high stagnation pressure on the front of the tire, and this causes a lot of drag, but you also increase the energy going down into the contact patch, which will increase your tire squirt. So you want to block off the front of the tire, but you'll note that on both this and the Valkyrie, the blocker is significantly narrower than the tire. Now, this is likely because if the tire is rotated in steer, this inside wheel face will come into line with this edge. We don't want to have a situation where we steer the tire and this inside edge is overlapping the tire too much, because then we're just losing energy to the inside of the tire. We're blocking off more airflow than we need to. So that's why this is smaller than the front of the tire. Because it's got this V shape too, where it's basically, you've obviously got a filtered corner, but it's still outwashing to the end more or less. It's still going to direct the air around that tire. So you can pick it up around the shoulder, and then on the inboard side, they can pick it up with the cake tin face, and the Valkyrie notably had a small little deflector on the bottom of its cake tin down here, so they can pick up that flow that's coming across there and use that to manage the tire wake further downstream. Now we then have this flat section in front of the tire. Now, often upwashing in front of the tire can be problematic for the same reasons that I discussed previously. You wouldn't do it if you didn't need the load on the car in there, and they've got this big double elements section over here so they can get as much load as they feel like through there. So they've gone flat here, which I'm going to guess is going to improve the overall effective downwash into the contact patch versus a cranked version, which should improve, again, any sort of tire squirt. It will also generate quite a lot of local load on it due to the low ground proximity, because this cranked cone section over here is going to be generating a lot of inwash. So there'll be flow coming in across that way as we go along. So obviously the flow is coming along, but it's also moving with the sideways component as it goes into the cone vortex over here. And so you'll get a decent amount of suction on this flat plate as well, even though it's not upwashing itself. This, of course, will cause a bulk mass flow to come around the wing, around the edge of the wing, like we see on all wings. And so these two outboard features are there to manage that. So you basically have the end plate, which is going to stop a lot of the mass flow going over. So you'll keep the high pressure on the top surface. You won't let as much mass flow bleed around. So you'll depower the bottom surface a bit, which can be important in terms of keeping the health and cleanliness of the lower surface. And you'll note that this particular end plate has quite a bit of camber to it. It's cambering that way. And that's going to help with the acceptance of the flows that are being pushed laterally outward on the upper surface. Now, the end plate is a delta shape. I'm not sure that this is the optimum shape that you go for. Adrian obviously spoke a little bit about how some of the features of this car are styling features. I'm not saying that the end plate shape is a problem. It's more, I'm wondering if they've made it delta shaped at no real aero delta in order to visually make it look a bit better, perhaps visually tie it into a modern F1 car. Lower down, this little foot plate curl will have a little vortex down here. Now, in terms of the direction downstream, it's a little bit tricky with these because depending on the inboard interactions, they can go in some pretty weird locations, but I'm going to guess that it's probably going to be crashing into the front of the tire, but depending on everything else that's going on around here, it might go much further inboard, or in some conditions, I have seen these actually stay outboard of the front tire. So no idea where that's actually going, but having this curled should be a lot cleaner and house the vortex in a more consistent manner than just having it flat. So like I mentioned before, this cone here will create a large vortex that will go downstream. The trajectory of this downstream will depend massively on the pressure field being generated by the devices behind it. But there's two potential routes they could essentially go with this vorticity. Either they could go and they could try ingesting it in the tunnel back here, and that would sort of stack with respect to the rest of the tunnel shape because they've clearly got a very large tunnel inlet. It's already coned and shaped in a circular manner. It would make sense if they were ingesting this vorticity in there and using it to boost the strength of the entire tunnel. That would stack. Another option is that it could be getting outwashed behind the tire in the sort of cavity there, but I'm not convinced that that's as likely, given there doesn't seem to be as many things that would be outwashing enough, far enough inboard in order to trigger that particular trajectory. Now, this vortex, as it goes further rearwards, will create a bunch of downwash alongside the side of the tire. It will get downwashing, but it will also generate a lot of inwash. So you can harness this downwash to improve some of your mass flow towards the side of the tire, which can help a bit with lower wake management, but right down at the bottom around the tire squirt and stuff like that, it can be quite negative as well. So that may have been managed by another device on the K-tin that we haven't been able to see yet, but that's the general gist of what's going on there. Moving a little further downstream, you can obviously see those stays and those front wing details that I was talking about earlier, but I just want to take a quick second to highlight its wheel discs. Now, these could very well change model to model. As has been mentioned before, this car is not the final version, it's just a static show model. But these particular discs with a thin outlet around the outside that allow mass flow to come out there could help with reducing the spoke drag, reducing the ejection of loss from the wheel, and that could help with this car's overall efficiency target because, like we discussed earlier, this is a very high efficiency car. So it'll be important to try and improve the efficiency where possible through devices like this, which are closer to a flat-faced wheel. Looking a bit further rearwards, I want to focus on the upper bodywork for a little bit. Now, you'll note that we have this bridging element out here after we have this large gap. And these elements bridging front and rear obviously are there to help connect this wheel pod here. But you'll notice that this whole section here basically transitions further rearwards into this downwashing side pod here. Now, this is not dissimilar to the setup that you'll see on current F1 cars, where they basically use the top deck flows and then channel them towards the floor at the rear. Now, it's divided a little bit in the center by the rearwards bridging element that's holding on the rear pod there. But you can see the general intent is to try and get everything down to the floor and the rear diffuser. You actually have a clear sight line on it, and the transitions are all pretty smooth, even both below and above that wheel fin. Looking a bit lower down, you can see the large barge board just inside of the front wheel. Now, as has been discussed a few times, this sort of feature is designed to create a large amount of outwash and basically kick the front tire wake that'll be sitting all here, try and kick that as outboard as possible to basically try and get it clear of anything that's going to be coming along the side of the car. We don't want to ingest this wake further downstream. We want clean air to everything else, and ideally all the air that's to the inboard side of this particular fin, we want to have that going downstream and feeding everything rearwards, feeding everything out the side of the floor and stuff like that. We don't want to be ingesting low energy tire wake into there. Again, if you look further rearwards, you'll find this particular end plating shape on the rear. The rear wheel pod is quite Valkyrie-like, but this end plate is a little bit different. Again, I'm not sure whether or not this is a styling inspired feature or whether this is pure aero. If I had to take a guess, I'd say that this is a styling feature. Again, I wouldn't expect a large aero delta on it, but it's just worth noting that this is unlikely to be what you'd pick if you just wanted a raw performance rear end. And why do I say that? Well, the overlaps are all a little bit strange in terms of having a delta that crosses over at that particular point. It's just not something that you would normally go for aerodynamically. Let's say you wanted it to be slatted, or you wanted to create a jet of air around there. You would normally align your leading edges so that everything would fix up, and you'd make a second element like that. You wouldn't normally go for this delta type shape. Looking a bit further inboard, you can see a few features of interest. One is this little bulge here, which I think is going to be the air intake for the cooling system. It's likely that this thing's going to have an F1 style radiator or similar in this particular region here. And then just a little bit further down, you'll see just how high that floor leading edges. That's the entrance to the tunnel there, and it's really tall. And let's go a little bit further rearwards so we can look a bit at this diffuser from the rearwards portion of the car where you can really see what's going on there. Now, the diffuser on this car is somewhat expectedly massive. It has a very similar visual to the Valkyrie because it's similar sort of size, but there's quite a few differences in here that I think are worth noting. Firstly, looking at the inlet, what you'll notice is that it has a curvature that goes with the narrower front down low that then outwashes there. Now, that's a little bit different to the Valkyrie, which went the other way. I'd guess that this is largely to increase the loading on the forwards portion of the diffuser, get that suction in the forwards portion of the diffuser, and power up any sort of vorticity that's coming off here. Now, what's interesting is that you can actually see the front wing cone that I was describing earlier. So if they are in fact shedding that cone vorticity into this tunnel, well, you can at least see where that's coming from. The diffuser doesn't gain much in height over the forward portion or anything like that, but it's worth noting that Adrian talks about in an interview about how forwards loaded this diffuser is. So let's work out where the forwards load is coming from. Obviously, we've got some of that more outwashing front that we were talking about earlier, but then also, if you have a look, this diffuser has a lot of lateral expansion as it gets further rearwards. Basically, the core where the driver is sitting and the passenger, that tightens up a lot towards the rear. And this lateral expansion will essentially increase the volume of the diffuser going rearwards, even though the roof isn't expanding that much. And this will create suction in the mid and forwards portion of the diffuser. As well as the fact that if, again, we are taking vorticity from the front cone, that vorticity will be more powerful the further forwards it is, so that will inherently lead to a more forwards loaded diffuser. Now, this diffuser's volume is more or less limited by the axle height of the car, because if you imagine the lower wishbone is at the line of the axle, so it's all the way up, and then the diffuser sits below that point there. So that's more or less limiting the height. However, once you get rearwards that point, rearwards of that rear axle, you can then start to expand. And this diffuser starts to expand very aggressively in all directions at this point. To support that expansion to that end, what it's got is this triple element setup, which I think is quite neat. So what you've got is that you've got your first element here, so that's your first split. And if you imagine that's like the whole diffuser of the first element, then you've got your second element here, that's your next split, and then you've got the third element just behind it there. And these elements are expanding in all directions, so basically maximizing your expansion there. As discussed before, we have a lot of clean airflow over the top of this diffuser. So every time you have a slot here, you're bleeding in clean airflow and you're allowing it to work like a multi-element wing, expanding out aggressively through this whole portion. The first split is quite low. The second split is much higher, and you'll see it comes further inboard over the top. So the first one seems to be just largely for the lateral expansion, just cleaning up any flows in this lateral expansion bit for the first portion. Then the second one, we're getting essentially a beam wing type effect by splitting it here and then expanding upwards as well as laterally. So I imagine this would allow quite a lot of diffuser expansion, quite a clean way. And if you have a look, this is expanding out behind the rear of the tire, and so that's going to push the tire wake outwards as well, pressurize this whole area, and that's going to suppress the tire wake. It's basically like a much larger version of the sort of winglets we saw on the back of F1 cars in the previous generation of rules. In the center, you'll spot there's a single fin on the keel, and this is an interesting one to ponder why it's there. Because if you consider a car just symmetrically in a steady state in a straight line, there's no real intent or purpose to devices dead along the center line. However, cornering and driving a car on a track is a little bit more complex than that, so let's run through some potential scenarios where this keel could be useful. The first one I'm just going to put out there is a scenario where you have a large amount of yaw across the car and you've got a large crosswind going across the car. Basically, that will push the airflow in towards the keel, and the keel will act to an extent like a shark fin. That, I think, is a fairly minor contribution compared to what I think one of the bigger things that will happen in yaw is that you'll have migration of your big tunnel vortices. One tunnel vortex will end up moving towards the keel, the other one will move away. Now, having the keel there will reduce this particular migration and keep each vortex on its side a little bit more, which may be a more optimum position. Given the overall annular shape of this tunnel, I would hazard to guess that it's quite reliant on the vortices being in the right spot. So that could be a potential thing there. Another thing to just discuss briefly is the concept of vortex meandering. If you imagine vortices in the real world like to do a little bit of move arounds, they sort of vibrate and sway all over the place, kind of like a wave. This is called vortex meandering. And again, if you have a diffuser where the vortex positioning is critical, perhaps adding this fin in the center would help with the meandering. Now, it's worth noting that, to my understanding, this car's only been done in CFD, not in the wind tunnel. CFD is not very good at meandering, so it's probably unlikely that this is the particular scenario. It's more likely it's your scenario, but it's just something I thought I'd throw out there anyway. Looking a bit higher up, you'll see this triangle-shaped portion. Now, I think that this is likely to be where the cooling air is exiting out the back of the car. Judging by some of the diagrams, it looks like the exhaust is going to exit a little bit further upstream on the top, even though we can't see that on the model. It looked like it from some of the mechanical drawings. But in the absence of seeing anywhere else for the cooling air to exit, I'm going to hazard a guess that this is its exit right in the center. While we're here too, you can also just see the brake scoops up there. And this is where the rear brake's going to be getting all their cooling air from. Again, because there's so much free air over the back of this car is essentially a single seater with a few pods strapped onto it. It's easy to just run an F1 style brake scoop for your brake. You don't have to worry about any complex ducting or hoses or anything like that. Moving a bit further upwards, let's talk about the rear wing. Now, the implementation of this is quite an interesting one because they've sort of combined it so that it aesthetically blends the rear wing into the rear wheel arches all together. So if you can imagine, the rear wing is essentially a sort of 1.5 element wing, I'm going to call it, where basically you have your first element sort of integrated into the wheel arches here, and it goes to sort of along here, and then you have a second element that is this black portion that goes along the back just there. And if you have a look in the rear view here, you can sort of see that first element go along there, and the second element just above it. Now, integrating the rear wing into the rear arches like this is quite a cool looking thing. I think it's a fairly neat implementation from an aesthetics perspective, but it does bring about some aerodynamic peculiarities that we need to discuss. The first one is that this particular portion just here around the wheels is a very interesting transition because you basically have to go to a leading edge on your wing here, and then as you go around it here, you have to work out exactly how you want to treat it. Do you want to try and lift it up to try and get as clean as possible a flow there? Or do you instead want to manage it through a sort of delta edge and shed some sort of vorticity or structure along here that will keep it relatively attached in this corner region near the arch guard? Now, looking at this geometry, I think they're going more for that delta approach, getting that vorticity off the leading edge and using that to keep the wing somewhat clean through that later portion. But it's certainly a more tricky junction than if you were to go and have a fully standalone wing element. The other thing that's worth noting here is that this wing sweeps around into the arch, which means that this portion through here, directly behind the rear tire, is going to be full of almost nothing but loss. There's going to be some energy coming through the wheel arch and over the top, but in general, you just got a lot of tire wake. So actually, the outboard portion of a lot of this particular wing section in here is not going to be doing a whole lot of work. But again, the alternative is to just have a wheel arch sitting there, which also isn't doing a lot of work either. So this may very well be a more efficient option in that particular region. Then obviously you have the 3D wraparound second element. Now this element is getting clean air the whole way around. It's got a slot gap across this bodywork the whole way around there. So this is going to be quite a potent element. It's getting clean flow. It's in good air. It's going to have good communication between the suction it generates and the diffuser. So it's going to drive the diffuser well. It goes the full width of the car and it's outwashing laterally at the ends. So we're getting that real 3D expansion going on there. And it continues the whole way to the ground. So they're obviously using this lower portion to manage this rear wheel wake and kick that rear wheel wake further outboard. And all of this is going to generate quite a solid amount of performance, and that ties into the very high efficiency that we spoke about earlier in the video. One thing that's worth noting though, and I think this is a detail that's probably going to change on the final version, is this particular centerline section here in the forwards portion. What you'll see is that it's got a very large expansion ratio. Basically, this whole leading edge stays flat across the front, and that means that when you have this downwashing central deck through here, you have a small area right along the center line, and then it becomes very much larger by the time you're getting towards the rear here. So there's the likelihood of having a separation or junction losses or overexpansion or anything in here is pretty high. I wouldn't be surprised at all if on the final version they have a curved leading edge that comes up a little bit more in the center to try and get better acceptance from the downwash from the center line of the car and trying to deal with that junction a little bit better. So a final note on something that I mentioned at the start of the video, which was the fans. Now, Adrian mentioned in an interview that they're going to be using fans and not in a manner that has previously really been used. Now, to my mind, that makes me think that what he's likely doing is probably going to be going for a blowing action that's going to go and suppress the rear tire squirt, whether that's located outside or inside the diffuser, but potentially using fans to blow and suppress that tire squirt and thus improve the performance of the diffuser. And one of the reasons why that comes to mind is because this is obviously something that Red Bull was known for back in the blown diffuser era. And you'd basically just be replicating the blown diffuser effect, but with fans, which would be a far more energy efficient means than just trying to suck out from this giant volume of diffuser. Because the problem is this diffuser is extremely large volume, which meant that if you just tried to suck out of it, proportionally, you probably wouldn't be making that much of a dent because it's not like it goes down to a flat floor or anything further forwards. The only other way you could potentially use fans is to just have them suck out from along the center line, which is the one bit of the car that is actually a large flat area down low. So if they're not doing that, the only thing that I could be thinking of is they're going to use the fans to try and do some sort of blowing effect. Of course, that's all a large bit of speculation, but it was the best that I could come up with. Well, that's all for this analysis. Thanks for watching. If you liked it, don't forget to hit that like button and subscribe to my channel for more content like this. Leave a comment below on what videos you'd like to see next from me, and hopefully, I'll see you next time.